In this section, we'll be talking about integration, which involves inverse trigonometric functions. Now, look at the form from the previous section. We understand that the derivative of arcsine u is u prime over the square root of 1 minus u squared. All right, so it should stand to reason that if the derivative of this is equal to that, then the integral of this is essentially that. That is, the integral of du over the square root of 1 minus u squared is arcsine u plus a constant. Now, generally, that certainly is the case, but you know, integration is the matter of pattern recognition. It always has been. We recognize a pattern and we apply an integration rule to that pattern and we come out with some kind of answer. Well, this is no different. It's just a matter of being able to recognize a pattern. Take a look at this problem involving differentiation, d or dx of arcsine x squared over 5. Now, using the procedures from the last section, we would understand that u is the x squared over 5. And the form for the derivative is u prime over the square root of 1 minus u squared. Pretty easy thing to calculate and to manipulate. Let's see, u prime. Now, we're thinking of this as 1/5 x squared, and so its derivative then is 2 times 1/5 x, or 2/5 x. And then in the denominator, 1 minus u squared. If this is u, then squaring, you see we get x to the 4th over 25. Let's manipulate a little bit. The 5 in the denominator here becomes a 5 factor in the overall denominator. And here we can create a common denominator. 1 is 25 over 25. So we have 25 minus x to the 4th over the common denominator 25. We can take the square root of this 25, giving us a 5 factor in a denominator out here, which is this form. The 5's go out. We have 2x over the square root of 25 minus x to the 4th. Now, pretty easy situation going in that direction, but think about the idea of being able to recognize this and the idea that we're going back to that, assuming that u is x squared over 5. That's the troublesome part of this. Let me put this up here a little bit closer, and I want to examine it a little bit more thoroughly. We have here for the derivative is 2x over the square root of 25 minus x to the 4th. Now, notice the relationship, the easy relationship of, let's see, 2x can be thought of as the derivative of this numerator. Okay, that's pretty easy. 25, gee, that's nothing but 5 squared. X to the 4th, that's the square of x squared. You see, so if we can somehow separate these two ideas, we can identify all of the elements here. And more importantly, we can identify elements here that give back that. You see, for integration purposes. Here's what I'm talking about. Suppose we change our problem and instead of thinking of x squared over 5 as u, suppose that x squared over 5 is considered to be u over a. You see, we kind of separate that fraction here, and then what we have in this derivative is this, but look at how easy the elements are to identify in going in that direction. It has the form of u over a. You see, if we have this u over a idea, then the elements over here related to u over a are u prime over the square root of a squared minus u squared. You see, and now we can go back in the other direction much easier. We can recognize a form for integration much easier. That is, the integral of du over the square root of a squared minus u squared is arcsine u over a plus a constant. Okay, now, so this is the form that we're going to be looking for integration purposes. I've repeated this last step up here. All right, for the integration, which involves, in the integration process, it involves arcsine. Now, because arcsine and arccosine differ, because the derivatives of co-inverse functions differ in sign only, we really only need to consider the major integrations which involve, or the integrations which involve the major inverse functions. That is, arcsine, arctangent, arcsecant. And these are all three of them. These can be developed from what we have talked about before, but I'll just give them to you here. Here's the one involving arcsine. This one involves arctangent. This one involves arcsecant. And notice the pattern that we're looking for in order to integrate for each of these. And that's the important thing. That's what we want to target here. And once we have met the pattern, you see, then we can go through and figure that integral relatively easily. Well, let's see. Let's take an example or two to become accustomed to this. Now, notice that this one does not involve a radical. These two involve radicals, and this one does not. So when we're faced with a problem like this, the integral of 1 over 2 plus 9x squared dx, and we're trying to meet one of these patterns, we don't have a radical here, and so we might tend to think, well, the pattern that we're looking to match is the one involving arctangent. All right, so we're trying to match that pattern, so we would come back over here and we'd say, okay, we need a situation of a squared plus u squared in that denominator. We don't have a radical, you see, so we're targeting this and we're trying to rewrite in terms of this form. Now, concentrate first on the denominator and then we'll deal with the numerator. So we want some value, some amount squared plus some amount squared. All right, let's go back over here. We can rewrite 2 as the square root of 2 squared, an amount squared, you see. We can think of 9x squared as 3x quantity squared. So we have the idea of an a squared plus u squared. Now, since we can identify the a as the square root of 2 and u as 3x, we know that u prime then would have to be 3 dx. And so we need a 3 dx up here. We need a factor of 3. All right, so we'll create that factor of 3 using a technique from before. We'll simply put 1/3 outside of the integration symbol and then a 3 in here, and away we go. We have met the pattern now. Well, now that we've met the pattern for the expression that we want to integrate, we want to meet the pattern for its integration, for the result of this. And it is 1 over a, just from over here, 1 over a arctangent u over a plus c. And we know that a, you see, the a is the square root of 2, u is 3x, and a is the square root of 2. So we just pop those values in. Now realize it's 1/3 of this, and this is what has this pattern. The 1/3 is tagging along as a sort of an outside factor. So we just kind of bring that down, the 1/3, and then it's 1 over a, that's 1 over root 2, arctangent, 3x over root 2 plus the constant. And we can manipulate this a little bit further. We would probably write this as a single fraction. We might even want to rationalize those denominators, but really it's not necessary. That's small potatoes compared to the other things that we have done here. Integration forms, which ultimately involve inverse trig functions, can be disguised very easily. So our task mainly is to target a particular pattern that we want to meet. Here, for example, if this is our problem, we would look at the problem and see which form this is closest to. Now, notice that we have a variable involved in this term. We have a radical here, so that kind of takes us out of the integration form involving arctangent. It puts us into the realm of either arcsine or arcsecant. It turns out that the one involving arcsecant is the one that we would target here. And the form we're trying to meet is this form. You see, so we want to write the form that we're trying to match kind of next to what we're talking about or directly underneath or something like that. Now, if we're trying to match this form, then it's pretty easy for us to identify, I think, the u and the a in this problem. The a is simply 1, and the u is, well, notice this is e to the 2x. So we can think of this as e to the x squared. So e to the x is the u. All right, if u is e to the x, then du would be e to the x dx. All right, fine. Now, let's try to manipulate into that form. We're taking this and trying to manipulate into that form, given that we've identified a and u. And that's the first thing we want to try to do, identify the a and the u. All right, now we'd like to put this into the form of, under the radical, u squared minus a squared. Well, the u is e to the x, so it's e to the x squared minus the a squared. All right, now we'd like to create a situation involving the other aspects of the form we're looking for. We need a u right here. Now that u is e to the x. If we're going to put a u here or an e to the x here, we have to have e to the x, but we need an e to the x up here. Oh, happy day. That's nice because that's exactly what we needed in our numerator. You know, the du, the numerator, du is e to the x dx. Aha, we have it here. So now we have met the form necessary, and the form for our answer, you see, for the integral here, is 1 over a arcsecant absolute value of u over a plus c. Just fill in the blank sort of here, and we have arcsecant e to the x plus c. Here's another one, and this one is made a little more complicated because it involves another integration procedure, another outside of the area of inverse trig functions. All right, it's this. This is our problem, and we might be looking to meet one of the patterns that we talked about before. Now, we have a radical in the denominator, so that kind of narrows it down to two of the possibilities. We have a constant here, an a hidden in here, and an x squared here, a u hidden in here, you see. So we would identify this maybe as an integration involving arc sine. All right, now that form is over here. We would be looking to meet this form. But we get into difficulty trying to create the du in this numerator when we have the x plus 2. But it turns out that we can separate this problem into two integration problems, thinking of two fractions here, the x over the denominator plus 2 over the same denominator. So we have the integral of x over the radical dx and then plus the 2 over the radical dx. All right, so two separate problems. It turns out that this one will easily meet that pattern and we'll be able to deal with it, and this one refers to information that we have talked about before. Now we would probably rewrite this, taking this radical in the denominator and write it as, let's see, 4 minus x squared to the negative 1/2 in the numerator. And now we think about integration using our power rule. Now remember, the power rule had to do with the integral of u to the n du is u to the n plus 1 over n plus 1 plus c. Now we're trying to meet this pattern here. Now, we would probably pick off the idea that the u involved is the 4 minus x squared. All right, if we let u be the 4 minus x squared, then du, the derivative of this, is negative 2x dx. All right, so we're trying to meet the u to the n du. U to the n is negative 1/2. Du is negative 2x. But we have x here. We need a negative 2 factor in order to meet this form. All right, to pop in a negative 2 factor, we'll have to attach a negative 1/2 factor outside of the integration. So it's negative 1/2 then, and then we have our u to the n du. You see, pattern met here, and now the integration is relatively easy. Bring down the negative 1/2, and we're then writing this pattern. We're writing u to the n plus 1. U is 4 minus x squared, n plus 1. The n was the negative 1/2, and plus 1 makes it 1/2. So this is u to the n plus 1 over n plus 1 over the 1/2. And then cleaning this up a little bit, the 2's take each other out, so we have negative square root of 4 minus x squared. Now I've stayed with this part of the problem to follow through with it with our thinking. Now we want to kick our attention over to the other part. So we're thinking about meeting this pattern which involves in the integration arc sine. You see, and the pattern is easily met here, letting, let's see, the a is going to be 2. The u is simply x, so du is just 1 dx, or simply dx. All right, so we have our pattern met here from above, and notice that I've taken the 2 and just kicked it out in order to meet the pattern. So the form that we want here for the integration is arc sine u over a plus c. So we'll bring down the 2, and it's arc sine u over a. The u is x, so it's x over the a of 2, and then plus c. Just bring that down, and this then is our final answer. Here's another one. This one, by the way, is a pretty tough problem. I mean, it's tough to see through and to recall all the things we have to see. But if thinking carefully through it and keeping things organized, it's not too awfully bad. Here's another one. It's this. Now notice the denominator has no radical in it here. And if we're trying to identify this or associate it with one of the inverse trig functions, then we would associate it with the one not involving a radical in the denominator. Which one is that? Well, that's the one involving arctangent. And that one involves this pattern. So we're trying to meet this pattern for this problem. This involves the sum of 2 squares. But here we have a polynomial, a quadratic polynomial. But we can complete the square here and create that kind of situation. We can do it like this. Just separate, you see, just kick out the existing constant, and now we want to invent a new constant which will give us a binomial squared, completing the binomial square. That's what we're doing here. All right, half of 4 is 2, 2 squared is 4, so we're adding 4 here. But if we add 4 here, we have to subtract 4 out here to maintain our balance. And factoring, we get x minus 2 squared. 7 minus 4 is 3. All right, now we're just about there. We can start to make some identification about the a and the u. Now notice that the u involves an expression involving a variable, and that's here. That's the first item in our fractional form, or in our denominator. But here in our form, it's the second item. So we're going to want to think of swapping these around. All right, that's fine. And the a then is this item, or is in this item. Gee, we want to write this as something squared. Well, that something needs to be the square root of 3. So we identify a as the square root of 3. The u is the x minus 2, and du is simply 1 dx, or dx. So we rewrite to this form, and now we've matched the form that we were targeting from up there. And now we want to write the integral, and it has the form 1 over a arctangent u over a plus c. And we just pick up the values of a and u from over here, and we have 1 over root 3 arctangent x minus 2 over root 3 plus a constant. Here's a problem involving a definite integral. It says, find the area of the region bounded by the graph of this function, the x-axis, and the lines x equals 3 over 2 and x equals 9/4. So that area is found from performing this operation. Now we're looking for a form for integration purposes that this meets as well as possible. And it'll turn out that we're attacking the form, the integration form that involves arc sine. And that form looks like this. Well, notice here we don't quite have that situation. We generally have a constant squared here, and we have some expression involving a variable here. But the point is we have the difference of squares. And when we have a quadratic form, or a part of a quadratic here that we can work with, we can manipulate this into that form. And let's take a look at that manipulation. I'm just going to take the radicand here and reproduce it up here. Now we would think about the squared term appearing first, so I'll just rewrite in the other order, and now away we go. Our object here is to complete the square and create the conditions for the form that we're looking for. So we'll do this. We'll force the factorization of the minus sign. We'll take the minus sign out of these two terms. Now I'm writing this with a bracket because I want to think about the problem like this. I want to think about having a trinomial, you see, that I'm going to turn into a binomial squared, and then I'm going to have a part over here in order to negate whatever I add here, I have to subtract there. That's the idea of writing this form. All right, now let's see. I take half of 3, that's 3 over 2. Square it, that's 3 over 2 squared. So I'm adding 3 over 2 squared right in here. it's a little messy, but I think we've seen this enough before to where we understand what this is. And we're going to subtract that amount right here. You see, and now when we factor, this factors into x minus 3 over 2 squared. And then we have minus 3 over 2 squared. And now, with this minus sign involved, let's go through and we have this. But you recall in the form that we're looking for, under the radical, it was a squared minus u squared. So we would think of this as 3 over 2 squared minus x minus 3 over 2 squared. And it's easy to identify then the a as 3 over 2 and the u as x minus 3 over 2. All right, so let's go back to our idea of area, and we have rewritten our radicand like this from right down here below, and we've identified the a as 3 over 2, the u as x minus 3 over 2, and du then, the du is simply 1 dx. All right, so now with that in mind, we're trying to match this form. The form we're matching is the integral of du over the square root of a squared minus u squared. Yes, we have that. And we know that this gives arc sine u over a minus c, plus a constant. Of course, we don't have to worry about a constant in a definite integral, but it's the idea of matching this form. So the area then is arc sine, you see, of, let's see, it's u over a. Now the u is the x minus 3 halves, over the a is 3 halves. And here's our integral, or our interval over which we're making the calculation. So it is arc sine of, let's see, replace x with 9/4, and we get this. And then minus arc sine, replace x with 3 halves, and we get this. Notice 3 halves minus 3 halves is 0, so this is arc sine 0. Here, to clean this up, what I did, I was thinking about just taking this complex fraction and multiplying it by a big 4 over 4. So 4 times 9/4 is 9, 4 times 3 halves is 6, and then 4 down here gives us 6. 9 minus 6 is 3, 3 over 6, that's 1/2. So we have arc sine 1/2 minus arc sine 0. Arc sine 1/2 minus arc sine 0. The arc sine of 1/2, the angle whose sine is 1/2, is pi over 6. And arc sine of 0 is 0. So pi over 6 is approximately 0.524, and that is the approximation for our area. Before we leave this part, I want to mention to you something general, something conceptual about integration and differentiation. We've developed rules for integration by looking at differentiation. We have seen that this idea of integration is just kind of the reverse of differentiation. So we just kind of match patterns. We look at differentiation, we say, if we can match the pattern over here, then we can integrate and just work kind of backwards. Well, that's fine, and that's basically how we approach integration at this point. But there are some extremely elementary, simple expressions that we can't integrate simply because we haven't encountered the patterns that they form. So a lot of work still is yet to be done in the area of integration. Now this topic, this idea, is addressed in your textbook at the end of this section. And I invite you to look at the list of integration rules. We've listed them before, and we would need to add the 3 situations that we've encountered in this section to that list, but we've seen it before and it's listed in your text, and I want you to have easy reference to those forms as you work through your problems. But look at, in that same area, there is a small list of examples illustrating what seems to be very difficult problems that we can easily integrate, and then some that are very, very simple, which we can't integrate at all because they don't simply fall into one of the forms that we've studied before. It's a rather interesting situation, but we will get back to this idea of integration in a future chapter.